Now we're ready to solve our problem of climbing staircases in the most general manner possible. Let's start terminal and go to desktop. Fire up Emacs. Create a new Racket file. Okay. Let's make the font a bit bigger. Control X plus. Makes the font a bit bigger. Okay, let's split the screen like so, and we're ready to go. I'm going to use a lot of comments this time. Let's use comments. Every Racket program, Racket programs start like so with this Racket line. Okay, and of course comments begin with a semicolon like that. You can do all sorts of comments, 1 or 2 semicolons, and you can put something. You can comment your code, like that. Okay, now we have to run it. Let's load it and run it. Okay, there we go. Just a minute. Takes a bit of time, Racket, to run the first time. Let me increase the font here also a little bit. Maybe I got this up a little too much. Could put it back down a bit, like so. There. That looks all right. And save it. Okay, now what are we trying to do? Well, we're solving the problem in the greatest possible generality. We have n steps, and our climber, our stair climber, can take anything like this, anything from 1, 2, 3, all the way up to p steps. So this is really general. In the case of p is 2 or p is 3, well, we have done these in previous videos. And we have looked at the theory of doing p steps like this. We have looked at the theory of this in the last video, and now it's time to implement it in code. I'm going to need a lot of tools. Let's see. First thing I'm going to need is a way to sum elements of a list. Okay, how am I going to do that? Well, there's different ways. I could use apply, I can use all sorts of stuff, I could use recursion, but let me do a nice, very attractive way, and I'm going to use fold left, define sum of my list. I'm going to fold left with the operation plus, start it off at 0, the sum, and there you go. Okay, let's try that. Sum 1, 2, 3, 4, 10. Good. Now you may think, well, I don't understand how that works. Alright, so if I show you another example, something like this, I am certain that you will now understand what's going on here. Just look at this and compare to the previous one. Fold L, multiplication, 1, accumulator starts at 1, my list, like that. Alright, let's try that. Instead of sum, I'm going to put product, and 24. You see? You get it? Now, before I continue with this, I want to turn on Paredit. Paredit gives me superhuman powers of editing Racket code, so you should use it. I'm going to use Paredit every time because I really like Paredit, and you should learn it too. It's a bit complicated to learn at first, but maybe I'll do some videos on it. Now, the next thing is that our state variables Well, they're going to be like A, B, C. There's a lot of them, and they go on and on and on. There have to be P of them. P could be anything. There will be P of them. Okay, and P could be big. Like we're going to try it with 100. Like the guy can take 1, 2, 3, up to 100 steps in one shot. So P could. You got a lot of state variables. We will keep the state variables in a list. We will keep them in a list, and we need to be able to add a state variable at the end. We have to add a new one, like the sum. All of this, as we saw in the theory portion at end. And how are we going to do that? Well, I'll just do a really simple thing. Insert at end of list, my list, and some item. How do we do that? Well, I'll use append my list list item. So I made this a separate function because this is a lot of function calls, and it would clutter up my code if I put it right into my main problem. Let's try this. Insert into this list, let's say the element 4. Yes, okay, it works, great. So I've got that, I've got this. I need to be able to generate initial conditions, and as we saw conditions, and as we saw in the theory portion of the video, we need P of them. They always going to be starting like this, like so. 1, 2, 4, powers of 2, as we saw, and so on and so on and so on. P of them. Okay, great. I can do this with functional programming. I'm going to use map to do this. Define initial conditions. How many do we need? Well, we need P of them. Let's see. Map. I'm going to map a lambda n exponential 2 power n onto a range. Wait, like so, onto a range. Hold on, I'll tell you what range does. P. Okay, how's that? First of all, what does range do? Let's say P is 3. Let's say P is 3, okay? Range 3, 0, 1, 2. And does this give me correct initial conditions? Initial conditions 3. Yes, 1, 2, 4. If there's 1, if he can only, if he takes, if there's only 1 step, there's only 1 way to do it. If there's 2 steps, there's 2 ways to do it. If there's 3 steps, there's 4 ways to do it in all. 1, 2, 3, 4. It doesn't matter how many steps he takes. There's 4 ways to do that. So that's my initial conditions. And I'm ready to write my main function. I'm going to use a closure. This will make a staircase function for me. So for example, all right, let's say my problem is P equals 3. The guy can take 1, 2, or 3 steps. Then I make a function. From this, I make a function F3, let's say, that solves the problem for n steps. And you can call it like so, F3n, or call it the Racket way. Okay, we'll call it F3n. This will give you a number of ways to climb n steps, taking 1, 2, or 3 at a time. Okay, we're getting there. Define. All right, let's call this make staircase function. Closure. A nice technique, very beautiful technique. Lambda. We're going to return a function of n. Now, how do we do this? Well, let's begin with initial conditions. Let loop. Now, our counter has to go from 1 to n, just like we saw in previous videos of theory. I will count up. I'll give it an explicit name like that. And the state variables are all going to be inside some list. And what list? Well, initial conditions P. There. That's how we begin. That's how we begin. Let's see if I can move this a little bit. Oh, yeah. Beautiful. All right. So that's how we begin. And let's continue. If we reach the end, if counter equals n, then I return what? Well, you know that A was the first, where are we? The answer is in the first one, A, you see? As we saw in the theory portion. How do I get the first one of the state list? Well, car, state, you see? And if not, well, we have to do the loop recursion. Up the counter by 1. And now, how do we update the state? Well, we have to make the new A B, and so on, and then add the sum of all the state elements to the end. So what we're really doing is left shifting the entire list of state variables, and then appending onto it the sum of those state variables. And that sounds complicated, but the idea is expressible very elegantly in Racket. Okay, I want to insert at end. We're going to insert at the end of the CDR of the state the sum of all that state stuff. Sum state. There. We did it. This is this is the staircase counting function. Now let's try it. Let's define F2 to be make staircase function. Sorry, I don't want to do that. I want to do code completion. Make staircase function. I need to. Maybe I'll reduce the font here a little bit. Okay. Hang on. Okay. All right. That looks good. Now, we're going to make the staircase function, make staircase function of 2 steps. 1 step or 2 steps at a time there. We have a closure, F2. Let's apply it. How many ways to go up 10 stairs, taking 1 or 2 steps? 89. That's what we had before, remember? Okay. And how about taking 3 steps? Well, we can do that. Let's define F3, taking 3 steps at a time. And do you remember what it was? F3 for 30? Do you remember that number? I remember that number. That's that number which I knew for a certain reason, which if you can guess that reason, maybe you'll win a prize. Okay, so think about that. All right, now let's go all the way. Let's say our guy can do, oh man, he can do 100 steps. He can do anything from 1 step, 2 step, 3 step, all the way up to 100 steps. Okay, and let's create this function. Make, let me go down a bit, need more room. Make staircase climbing function, code completion, P is 100, there, F100. Now, how many ways can this guy climb a staircase of 1,000 steps? Oh boy, that's F100, 1,000. There. No problem for our computer programming kung fu. This was a totally awesome problem. Okay, I really enjoyed thinking about this. We solved the staircase problem to a degree that most people never see or want to think about. I think there's a lot more to say about this problem, and I will revisit it one day. But if you like all this stuff, click like on the video and subscribe for more computational kung fu. Good night.